What are geostationary satellites? What could we do with them? And why can you hear Portuguese speakers on an American spy satellite, military satellite? Christian Berger is giving us an introduction to the technology and use of satellites. You may know him from Hacking the Bus. Christian, your talk. Hi, welcome to my talk on geostationary satellites as a hobby. If you, after a citizen band person, it's really hard to, it feels insignificant. But I need to start my talk about an introduction to signal technologies and principles. There are two ways to present them. A signal that changes over time, as we see on the left, and a signal on the frequency range, which we see on the right hand. A sinus wave in a frequency, a sinus has only one frequency and nothing on the rest. If there's a more complex signal that's not repeating itself, and there you have like a band of a frequency that is like occupied by the signal. This is relevant for the later topics. You can see the frequency, or you can modulate signal on frequency level. There are low pass filters that only pass low frequencies, high pass filters that only let high frequencies pass, and band passes that only certain frequencies pass. A mixer, there are various ways to show them, but in our talk, all these signals are a mix of a sinus wave. It's a multiplication of a sample. So let's talk about a sample in a digital way. And if you multiply that with a sinus, that gives you a signal at the exit. And the sum and the difference of these frequencies, and you can picture this as if the signal is shifted and mirrored. So the right signal is the mirror of the left signal, but it's the same signal. If you add a band pass filter before or even after it, you can shift the frequency of a signal. That's very useful, and I will mention it a lot in this talk. First, why do you do that with the satellites? As you know, the Earth is a globe, it's a sphere, as you can see in the picture. If the left sender wants to contact the sender on the right-hand side, it would need to go through the Earth, and this is very difficult. Luckily, for some frequencies, roughly below 30 megahertz, that the ionosphere reflects these signals and from the Earth, and that bounces up and down, and you can pass a longer distance. The citizen band people know a little bit more about that. But it was also used for phone lines. These are pictures of the 50s, shortwave connections between Frankfurt am Main and New York. There were about 5 channels and telegraphy channels. That was technology of the 50s, so that's why it's a little bit bigger. But how well does that work in practice? In the same article where I took these pictures, there was a beautiful diagram. That's the signal strength that was received in a diagram. And the scale is logarithmic. in decibel. So one line is 5 decibels, two line is at 10 decibel. And you can see it is from 0 to 0 minus 30 decibels. So that's like lower by a potential of 1,000. That's interesting for somebody using a radio, but it's not very interesting for a phone call because the quality drops, and that's not good for a phone call. So if we could have a satellite up there, if you have an object, if you hold it up and you loosen the grip, it drops because of the gravity. Luckily, there is a workaround for that. You can compensate for gravity on a curved. You have the century pedal force. You know that from an open bottle that you swing over your head and nothing is coming out. And you can cancel out the gravity and the centrifugal forces. They will stay in this orbit forever. You can calculate that. This is a little animation. It's at scale, actually. If you zoom closer to the planets, the orbits are getting faster, and if you farther your way, the slower the orbits are. You can't really see the colors well, but the outer orbit, that's the geostationary orbit. And the satellite is exactly as fast as the Earth. You can see that the texture of the globe. That means if you're on the planet, the satellite appears to stand over a point over the equator, always at the same point. That's enormously practical because you only have to adjust the antenna once, and you always have like the connection to the satellite. There's one small problem. It's quite a distance. It's about 35,800 kilometers to a geostationary orbit. So basically, only the man who flew to the moon covered that distance. Otherwise, that distance is pretty far away. And there's actually no space others who could do the maintenance of the satellites. So that's why they try to keep those satellites easy to maintain and as simple as possible. That was why they came up with the idea of a bent pipe signal. The idea is to send up a signal in one frequency, and it is sent back on a different frequency. It's most simple. It's a very simple construct. It's just a filter. You mix it and you amplify it. In reality, it's a little bit more complicated, and you have redundant parts in there. But that's a simplification. And this allows you to send signals even though you don't know the specifications yet. That's also very handy because when we changed from analog to digital TV, we didn't have to replace the satellites. Now, there are some people who listen into military satellites. Usually that's encrypted, but 1997, somebody was listening in and they heard. And now we should hear sound. It's not a very military sound, isn't it? It's what happened there? In Manila, there's a radio station, my FM, that was what we were listening to. And if you're building a sender and it's not perfect, it's not only sending on its frequency it's designed for, also on the multiples of this frequency. There are various factors that can influence that. There can be rust, for instance, can cause this. So on a professional setting, you try to avoid this and reduce the risk for that. But this happens. And this happened to this radio station over several weeks. And it was sending on the receiving frequency of this military satellite. And the satellite just returned the signal on a different frequency. And it was audible here in Europe. The military could have technically shut down the transponder, but they didn't care, and that's how it is, I suppose. This was an accident. That was not an intention by this radio station. But you could do this intentionally. For instance, if you're working at a TV station that's operating an uplink station that has the ability to send up signals, and you could send up a payload. You take over the transponder because you're sending stronger than the original signal. And you can complain about the billing structure of this pay TV channel. And this person made it for over a couple of minutes. They could identify him over the font the text was generated with, and he apologized. He was very sorry for this stupid idea he had after work. But now, next idea is satellite piracy. This is rarely done over TV satellites because that's rarely the case because the companies are too big and they will certainly complain and take legal steps to defend. But US military satellites, nobody seems to care if they are being used by other people. And therefore it was for a long time, I'm not sure if it's still the case, but on some military satellites on 255 megahertz, you could always hear Portuguese, Brazilian speakers having a phone conversation. But I understand it's possible. You can just modify a signal, and an amateur radio expert can achieve this. But to talk to satellites, you need some sort of antenna, like in every kind of radio communication. If you're clearly below 1 gigahertz, the smartest way is to use a Yagi-Udo antenna. Mr. Yagi translated the work of Mr. Uda. That's why it's called a Yagi antenna. These are the classical TV antennas, from back in the days. One stick with a few sticks on a cross, more or less the same distance from each other. That's how you can an antenna with a moderate directional property. Or you can build multiple antennas. That's like a grid antenna. That's the advantage. It can be very flat. Satellite phones, for instance, use these kind of antennas. And some other satellite internet providers use these flat grid antennas. But the classical antenna is the parabol antenna, the satellite dish. It's a parabolic formed piece of metal that bundles the signal into a single point. That's one in Reisding. It's inside the globe, and that's just to protect the antenna. In this case, rain and snow. Because that's bad if you have that on expensive equipment. And nowadays, in a military use case, to prevent the enemy to see where the antenna is directed to, and with that dome, you can just protect that. For me, it looks like these these are two innovations. The receiving units are like at the bottom, and you have an additional mirror with a weird form that shortens. You can build it in a way that the curve around the orbit are lined up, and you can see the receiving units with the orange cup on it. And you can, for each position, you can have one receiver. And back in the days, they were a bit bigger, and the receiver unit was still in the middle, in the center. At this size, it doesn't really matter. It's probably easier to manufacture. The disadvantage is if the unit, if the receiver is exactly in the line of sight of the satellite, however, it creates a shadow that prevents the reception. That's how you can see the installation of the receiver unit. This is a video from 1987, and it explains how to set up the horizontal and the vertical adjustment, and you merge them over a coax relay into a single line. And
einer kartfreien Satellitenempfangsstation für Sie als Fachhändler oder Installateur wirklich kein
an explanation on how easy it is to install this satellite dish. The satellite dish can be set up in a harmonic way for you in your garden. Back
They used to use a very big dish. Now it's smaller, but you still need the receiver. Now, with the common satellite, this is somewhere between 10 and 13 gigahertz. That's hard to work with. You can send it through a cable, but then they get very expensive and you can't bend them anymore. And if you bend them accidentally, they're broken. They cost 100 euros per meter, that sort of thing. And that is why we're using the mixer. You see here, you amplify, you mix, and then and that is you shift it down to 1 gigahertz. This one has 4 exits. That's 2 frequency bands. Each one horizontal and vertical, and downscale to 1 to 2 gigahertz. If you have a simple one, then you have a switch, and you can choose the one or the other. The technology from today on what you send is typically called the digital video broadcast. Comes from the television world. You have a modulator, and that sends it to the transceiver, and that sends it to the satellite. So basically, the input comes from data streams, from audio stream, video stream, and their constant bit rate, and then the multiplexer joins them, and you can also add other data, which is the lowest arrow on the left might be subtitles, metadata, whatever. This is the MPEG transport stream. It's a little bit like a network protocol. The packets have a fixed size of 188 bytes. They always start on a 47, hex 47. They have a header with a PID field that has 13 bits. And that PID number is the identifier of the data stream. And you simply select, I want this PID or the other one, and then you ignore the other ones. You can make a transceiver like this for a single program. That's what you see here. That one was created during the Corona problem, and it came from a delivery van. And now she wants to say something to us.
Ja, aber ich drehe den Ton ab, weil ich das.
I am turning off the sound because I find it bad and I don't want to talk about it. I don't want to talk about this. But for you, I'm saying that we are talking about a German politician. So, this was a media critic without intent. Now, at home, in my home, it looks like this. I think I have 10 LNBs, and I always put 4 into a single concentrator, and then into an input board on my PC. So it's a fairly simple setup. I do this in order to archive teletext. Somebody has to do it. So yes, thank you for the applause. So if you want to have Finnish teletext from yesterday, 1300, I have it.
Es gibt dafür eine sehr praktische so eine Art Mittelware,
very functional middleware which watches these input boards and all the metadata that is being sent. The general idea is you make an API, you ask it for all the multiplexes, and then you get a JSON document that gives you a list of all of them. And here you can see the block with the services, and they are UUIDs. You pick a certain UUID, and then you ask the API again, give me that UUID. And then on the right-hand side, you see the answer, which where the service name is from the alternative SWR, and then it contains multiple audio streams. And if I want to have that stream 802, then I make another call to another API endpoint, and then I get the data stream. Finally, there's an amateur satellite, and it's in a geostationary orbit. I'm not saying the name. You can read it here. And you can, I'm giving you here the uplink frequency where you can send it up, and then you can see where it comes down again. That's it. Here's my contact information. So if you would like to have something like this, if you want to build one yourself, if you want to try out mine, please contact me. I will work with you. Thank you.
Sehr schön. 255,55, diese Zahl habe ich mir gemerkt.
255.55, that's the number I remembered.
Vielen Dank, Christian.
Thank you, Christian. I expect some of the audience have questions for you.
Ich fange an mit den Fragen aus dem Internet, da gibt es tatsächlich...
Well, let's start from the internet questions.
Also erstmal nur eine Frage, aber wie konnte denn der Testbildsender über die Schriftart überführt werden?
How could the pirate be found via the text? Well, he used what technology was there. He had a generator.
Man muss dazu sagen, das war in den 80ern.
It was in the 1980s. So he was mixing two things. He was mixing the standard test image and mixing it with typeface. So these machines were made in the thousands, and then they looked where were they delivered, which station got which, and what has an uplink station and so on. Where did it come from? Now another question for the recording of the video text. So if you have 10 LNBs, are you sending 40 channels? The answer is there's not a real limit. So my 4 exits, 4 outputs from the LNB, and I have a multi-switch, and my decoder card can receive from 4 transponders at the same time. And a single transponder can deliver somewhere between 10 and 40 channels. So I can get all the teletext streams, and then I make files with just the teletext. Another question. A geostationary satellite can be seen from many places on the Earth. So you can send from many places. And so this amateur satellite, that one does accept input from all sorts of places at 2.4 gigahertz, and it'll shift to 10 gigahertz and deliver it down. Now there's many amateurs that want to use it. What happens when all of them send something? Where is it being sent? How does the footprint work? Where does it send it to? Can you say something? Well, the answer is that the antennas are directional, and there's a strong focus on Great Britain. In Bavaria, you can't see it. In Hamburg, you can see it. In the Netherlands, it works nice. But these amateurs, you cover the whole Earth, so that everybody who is on a visible line to it, that's a third of the Earth's surface. But when you talk to Chaos Welle, they will probably have a better answer than me.
Vielen Dank für den Vortrag, war sehr nice.
Well, next question. Thank you for your talk. It was very nice.
Wie groß ist denn so der Datensatz, den deine
Now, how big is the data volume that your teletext archives per day?
Es ist, glaube ich, irgendwie so ein Gigabyte oder so.
I think it's about a gigabyte.
Jeder Teletext ist quasi ungefähr
Every teletext
so 1 Megabyte groß.
is about 1 megabyte in size, 1 to 2 megabytes.
Ein paar hundert Kilobyte. Es hängt stark davon ab, wie man es dann zusammenpackt.
So it's a question on how you pack it. If I make tar GZ,
dann fällt es auf den Faktor 10 zusammen.
then it shrinks by a factor 10,
Pro Monat ungefähr so 20 Gigabyte oder
and
so.
I make about 20 gigabytes a month. So there's monthly dumps on archive.org where you can read them.
Als Anschluss zu meiner Frage von gerade.
A continuation to my previous question.
Geostationärer Satellit ist ja eine begrenzte Ressource.
Now, this is a limited resource, the geostationary satellite. Seems to me that 100 amateurs sending something, there's a lot of noise coming down. How is this being coordinated? How is it being modulated? How can it be differentiated? Well, the answer, they are strong transponders. There's rules in amateur radio. In shortwave, there's also a limited number of frequencies, and they have their ways of agreeing. So talk to Chaoswelle, and they will tell you how they coordinate amongst themselves.
Hier.
Hi, vielen Dank für den Vortrag. Hat mir
Thanks again for your talk. I really liked it. I have a technical question.
Wie kommt es überhaupt, dass man mit 2,4 Gigahertz hochsendet, aber dann
How can you send with 2.4 gigahertz and then it comes back at 10 gigahertz? Is there a reason why that factor was chosen? Yes, of course, you can shift it by any amount that you like. And it was probably chosen because 2.4, there's an amateur radio band, and it's also it can be handled easily. We can build technology for it. And the upper frequency is just below television satellites. So you can take that technology, and it's a practical question. There's close technology that can be adapted. So you easily get that technology, and that's probably why those two were chosen. Another question from the internet. Are you planning to make a Git from the teletext pages so that we can see changes, updates? Yeah, I've thought about it. It's a little bit of effort. I thought about it. My archive goes back by 10 years. I'm not sort of a Git expert. How you make a Git commit going back in time. And then there's also the question of the legal. It's called teletext, but it's not ASCII. It's a close relative. But you have columns, you have a few special characters, so you would have to pre-process it so that you can see something. But if somebody is interested, please come to me and we can talk about it. I can send them somewhere. Another question. I seem to remember that satellites are dumb in sending down the signal. Yes. Yeah, I think you can get the frequency of all satellites because there's manuals. There's some licenses and a technical regulation. I guess you'll have to look them up. Perhaps even a listing in the internet. Now, another question. Who's operating an amateur satellite and why is it available? Excellent question. As far as I know, there's amateur satellite communities. Now, I don't really know this, but my assumption is they built them and they were given to NASA because NASA also works with radio amateurs. And that specific one was sent by the Kingdom of Qatar. Somebody in a high position seems to be a radio amateur, and he just put this in. AMSAT, I believe it's called. Now, geostationary is very far. You can't just simply add it as a payload. Well, I'm not sure about the details. There's special electronics in there for amateur radio.
So, ich glaube, das war's mit den Fragen.
Questions are finished.
Also ich bewundere es sehr, wie detailliert du dich damit befasst hast. Also selbst ich bin neugierig geworden, habe mir deine Kontaktdaten.
Even I got interested, and I've noted down your contact information. Thank you again for your talk, and all the things that you do and with the satellites and what we can do with them. An applause, please. Thank you.